Hi, this is Miss Litton, and this is my wonderful Period 3 AP Bio class. Say hi. Hi. All right, so we're doing senses, and keep in mind there's very little on this you actually do have to know and remember and love and take with you. However, the last chapter on the nervous system, was that one of the ones you needed to know? Yes. And if you look, I gave you the learning objectives in your group shared notes, and it talks about learning objective 3.44, the student is able to describe how nervous systems detect external and internal signals. Okay, so even though this isn't a mandated chapter, this is how are we going to detect external and internal signals. We have to be able to use senses. Okay, so we have to talk about how it relates to that. So this is very obviously connected with our last chapter because this is what's going to trigger those particular neurons. So it's all about homeostasis is what you want to look at. We're always trying to maintain homeostasis. So locating nutrients, you have to know where the food is. You could smell where the food is. You could see where the food is. You could hear the noises of the food. So you could think about other animals and they'll go and attack it. How to avoid danger. How to learn from previous experiences. All towards that. Take a look at this picture. Okay, so at first you might have just thought it was a man, and then you could see it's a photograph of a man that's cut, right? So what I want you to use right here is the idea of you saw that you had that stimulus that went to your eye. You received that stimuli, but your perception was different as you looked at it, yes? When you realized it's just a photograph of a man and then it was cut. And that's one thing you want to make sure you have in your head. We receive stimuli, but perception is interpreting the meaning. What does that mean? And this would be like we talked about those pictures where if you relax your eyeballs and look a little bit differently, that you can see some other picture. You perceive it the same way every single time. Okay? It's how we understand it, how we interpret that picture. Sometimes it looks like an old lady, and then you look at it again and it's just kissing. Right? Okay? And that's all has to do with perception. If somebody types in all caps to you in a text or an email, what do a lot of people perceive that as meaning? You're yelling at me. Okay? It's still letters that we're reading, but because you put it in all caps, all of a sudden you're yelling. Okay? That's our perception. Could you tell if somebody was mad at you even if they didn't speak your language?
Yes.
Yes, because you could perceive that they were angry. My old neighbor, bless her little heart, I don't think she's around anymore. It used to throw me, then I realized what was going on. She drew on her eyebrows. She didn't have eyebrows, and she had trouble with her bilateral symmetry organization because she drew them differently. So what happened sometimes is she'd have her head as I was talking to her one way, and I would interpret that as surprise because her eyebrows were drawn like up high on one side. I'm like, she's surprised about something. But then she could turn and the other eyebrows she drew like this. I'm like, she's angry, you know? And so I'm like, she's surprised, is she angry? Surprised. And I realized it had nothing to do with actually her being surprised or angry, but it was how I saw her eyebrows in that particular day because she wasn't consistent in how she drew them, okay? So it's how I interpreted that stimuli. So you have internal and external receptors for detecting your changing environment. So let's go back. Number one, define. Specialized cells or neurons that detect certain types of stimuli and communicate information to the central nervous system in order to maintain what? Homeostasis. Two, classification, depending on where the stimuli is. If it's an interoceptor, it's coming from inside the body. Coming from inside the body. Now, things we can detect inside the body are things like pH, and pH of the blood, blood pressure, right? We learned about different ways to combat that. And exteroceptors are detect stimuli from outside of the body. Taste, smell, also temperature. You can feel heat, right? You can feel the heat of a fire because you have receptors that can detect that. You can feel heat inside your body, right? If your own body tissues are hot, but you can detect external stimuli. When we think about eating, you're bringing food it's outside your body and you're putting it on your tongue and you're tasting that food, right? And then as you're tasting it, then you're bringing it, it's not inside until it's in one of your cells, right? Okay, so that's still an external stimuli. And then we communicate that information to our central nervous system. There are different types of receptors. The oldest, the most ancient, is a chemoreceptor. And in chemo, you think what? Chemical, right. Universal, most primitive sense are chemoreceptors. Primitive and universal. Some examples of chemoreceptors are smell, taste, and pain. Smell, taste, and pain are all chemoreceptors. A chemical is triggering that action potential. Yes?
How is pain triggered by a chemical?
Because the chemicals that are released from damaged tissues. Now, you have different kinds of pain. You have deep pressure receptors that, like if your mom was pissed at you and grabbed your arm really hard or something like that, there's deep pressure, but that can be pain. And even if you're overly cold, like if you were forced to hold ice in your hand and not let go, it would be very cold, but it would also trigger what? Pain, right? So sometimes one stimuli can trigger another sensation as well, you know, even though it's just extremely cold. Okay, some other chemoreceptors, planarians, whom you know and love, have little chemoreceptors out here on the sides. You have here, you have crustaceans who have chemoreceptors at the end. You have fly feet, and when flies walk on food, they're actually tasting the food while they walk on it. And it's not these pads right here, but I don't know if you can see this little horn right here. They'll have one on either side. That's the chemoreceptor. So the chemical, when they're walking on that food right here, okay. When they're walking on that food right here, little chemicals will bind to that, and that's how they smell. Okay, and for us, smell and taste are like the same. In fact, most of what we consider taste is really what? Smell. It's really smell. Does cold pizza and hot pizza taste the same? No, it's still pizza, right? So why does it taste differently? It's because when it's hot, more of the chemicals are evaporating up off that pizza, so more of them are going here to your nose, so you're smelling it better. When you have a cold, does your food taste as good? No. Okay? And the reason is the mucus are blocking the neurons, they're called olfactory cells in your nose, from being able to detect the food. And so as a result, the food doesn't taste the same. What you want to do is blow your nose a whole bunch and then eat, and then you're more likely to be able to taste that food. Okay? So fly feet, tasting the food as they walk on it. We have chemoreceptors in our nose as mammals and in our mouth, and we'll go over those. Okay, another, oh, here it is. There we go. So smell, taste, and pain are your examples. Mechanoreceptors is mechanical movement. Stretch receptors, balance. Okay, hearing is actually a mechanoreceptor as well. And this thing I wanted to show you. Okay, so I have these here. And if you wanted to check your BioBuddy, you've had this done to you, right? And the reason why this end looks right this flat and this is here, do you know what they do with this end? You ever had it where they run it along the bottom of your foot? Yeah. And they look to see if your toes curl, because that's what you should do when it runs along here. So that's what that's for. And then here, when they knock right here on below your knee, there's something called a patellar tendon, and tendons connect muscle to bone, ligaments connect bone to bone. And what happens is when they tap it, it pulls gently, on that patellar tendon. Then that patellar tendon pulls a little bit on your muscle. What's your muscle right here? What's right here? Hamstrings are in the back. Quads. Mm-hmm. And inside your quad, there's a little proprioceptor. It's a little spindle. And what happens is when the tendon gets pulled, the muscle gets pulled, and that gets pulled a little bit. And so it's a reflex action in response. Is if it's getting pulled, one way is to do the counteract. And so this muscle right here, your quads, contract and kick out. It would be the same thing if you took a flashlight and shined it right in somebody's eye when they weren't expecting. They put it right into the eye, a really bright light. And what's going to happen is your pupil's going to get what? Bigger or smaller? Smaller. And you've experienced this if you've gone to a matinee and then you walk outside and the light like, ow. And it's because your eyes have been dilated and now they're trying to respond to it as a reflex. And so your leg just spastically kicks out. Now, that muscle spindle is used every single day all the time, but not spastically. You know, we don't walk like that. But we do walk normally. I'm aware if it's getting stretched even a little bit, and I can counteract that in order to keep upright and not trip and fall all the time, right? That's part of that normal. You're just making it hyper when you do it, when you get it to kick. And they can just check to make sure it's working at all. And the same thing when they would shine a light in your eyes. Okay, so that is a mechanoreceptor. So on your notes, mechanoreceptors are mechanical forces. So it could be pressure, sound, balance, touch, and stretch. Okay, and I'm going to give you another example. Ken, can I use the back of your neck because it's exposed?
Sure.
All right. He's like, what am I going to say? So lean forward a little bit. Okay. So you're just going to tell me, like, hold out your fingertip first. We'll do your fingertip. Close your eyes. Don't look. Okay, got yours closed. Okay, tell me one or two toothpicks.
One, two, one.
How do you do on that? Really well, right? Good job. Okay. All right. Let's check right here. Go ahead and forward.
One, two, two, two. All right, that felt three.
Okay, close your eyes.
Two.
Okay. So is he able to detect as well one or two? No. And generally speaking, on the back of somebody's neck, it's about here where they can differentiate between one and two. But you saw on his fingertip, right? I had them super close together and he could still detect two. So why is that? What?
Not as many sensory
Yeah,
receptors.
not as many receptors there on the back of his neck as he does on his fingertip. So obviously, this these toothpicks are here and these are here. You can check anybody you want. You can check the back of their hand. What do you think has more, fingertip or back of hand? Fingertip. Yeah, exactly. You could check somebody's lips. You know, different areas we have more receptors concentrated because it has been an adaptive value to be able to determine that. Okay. Same thing as hot and cold. They're not the same. A lab you might do, you could do it in this class too, you can take rods and put them in cold water and put them in hot water and take them out and dry them and touch somebody and you ask them to close their eyes, can they differentiate between hot and cold? He couldn't differentiate between one and two toothpicks and I had it like this far apart and he's, you know, or just one toothpick and he's like two, okay, and it was just one toothpick, so it's hard to differentiate. He didn't say it like that, he didn't go two, but I was like, okay. What'd you say?
I was saying you might have given him the wrong answer on the chat earlier.
Oh yeah, I gave him all the right ones, except for one. That's the one he missed. Thermoreceptors are exactly what it sounds like. Temperature changes, skin, hypothalamus. So skin would be an exteroceptor, and hypothalamus would be a interoceptor, inside, right? So externally and internally, we're able to detect temperature. And then electromagnetic, like light, heat, the photoreceptors of the eyes. Okay, youngest bio buddy, you're on the spot. I'm going to show you 3 different pictures. How are they different? How are they the same? Okay, just interpret this. How are they different? How are they the same?
This one
No, just your bio buddy will hear your answer.
One, there's chemicals.
With enthusiasm.
The other one, there's the pressure, so it actually needs to be pushed on it. And then the other one's light, so it needs a light energy to come through. But after that, like all the stimuluses are different, but we actually
My question is, if I want to use energy, that's pretty weird, huh?
Pressure.
I'm gonna ask you this. I want you
Okay, so how are they different?
different stimulus.
Here's 3 different cells. How are the cells different?
Different stimulus.
Okay, not different stimulus, but different receptors, right? Different receptors. So this one right here is a chemoreceptor. This one is a mechanoreceptor. This one has what? Photoreceptors. So that's how they're different. They have different receptors. These are proteins in the cell membrane, right? How are they the same? Yeah, that signal transduction pathway. Okay? So I want you to see the beauty of this. Different cells, the interior chemistry of it, that process is conserved. What happens? Right? They open up an ion channel, some ion comes in, and it triggers then the next cell. So the internal chemistry is the same. The only thing that has to be different is the receptor. Okay? And what we're going to find out in the next chapter when we talk about hormones is the chemistry inside the cell. There's like 1 or 2 prevailing ways to respond to any hormone. But what's different are the different receptors. So this is why you can flood the body with adrenaline, but only certain tissues respond because they're the only ones who have the receptors for adrenaline. Okay, so that's a conserved process. Just change how you receive that information. This should give more credence to when we talk about the cell membrane decides what goes in and out. And not only what goes in and out, but how the cell functions, right? Because if you have the right kind of receptor for that particular chemical, it can trigger a whole series of reactions or what proteins are synthesized inside that cell. Right? So the process is that you have some sort of stimulus. That stimulus could be received directly by a neuron. For instance, smelling, your olfactory cells are true neurons. So the chemical itself is binding with the neuron and triggering an action potential. Or it could be a specialized cell that triggers a neuron, like it is in taste. Okay, so you have these taste cells, and if you reach that threshold on that taste cell, you will trigger then a sensory neuron. But either way, you're going to eventually have an impulse that goes to your brain and spinal cord, and there it's the same message like we saw. All neurons speak the same language. It's the destination in the brain, stimulus received, but then you have to perceive it too. And I don't know if we talked about this last class. I know I talked about one class, but remember if you ever watch Big Bang Theory and Sheldon, it's like, oh, somebody, what does he do for somebody who's stressed out and not and emotionally upset? He always offers them tea. Okay? He has memorized that response, you know, and he'll say, no, I don't want, somebody will go, I don't want any tea, and they're like, it's not optional. You're upset. You must have tea. So he's memorized the social response because he doesn't know. And he'll say, is this sarcasm? Or he can't tell the difference between if they're literal or sarcastic. Did anybody watch the movie where I like Groot movie? What is that called? Guardians of the Galaxy. Guardians of the Galaxy. I love that big guy that's kind of all tatted because he takes everything what? What? Literally. He takes everything literally. You know? Yeah. And he goes, nothing flies over my head. My reflexes are too fast. You know? And what they mean is, no, it flies over your head. So do you understand? He received that information, but he perceived it differently. He perceived it as literal. Okay? So he didn't know how to differentiate between that. So that's perception. Okay? On your process of sensation, you have stimulation, then you have sensory receptors, either a special cell or a neuron. A special cell or a neuron. An impulse is an action potential in sensory neuron. And then sensation is in the cerebrum. And then perception, interpretation of the meaning of what is sensed in the cerebrum. Interpretation of the meaning of what is sensed in the cerebrum. Can you tell if one of your parents comes home angry without them ever talking to you or without you seeing them?
Yes.
Okay? Can you communicate to your parents when you're upset or mad? What do you do? What's a way to communicate? Do you slam a door?
No.
You ever done that when you left a room? That probably you only do that a couple of times. And then is that tolerated in your house?
No.
Are you allowed to slam doors? No. These are ways, and then we interpret that meaning. Everybody could hear the sound, but you know what that means. You know, if you slam a door on accident, generally people go, "Oh, I didn't mean to slam that door." You know, right? You have to, because you know how that will be perceived. All right, next. Okay, oldest bio buddy, it's your turn. Tell them what this is about. Go ahead.
I'll take it. Don't look at me.
Okay, good job. I'm sure you did a great job. Different receptors. Okay, you can be whoever you want to be, as long as it's not mean.
Hey Max, monster.
Oh wow, dude, I'm so bad at this.
I'm so happy right now.
What's called classical?
What should I be? Who's Peter Yi?
Oh my God.
Peter Yi is a savage.
What?
Peter Yi.
Okay, I'm going to pause this. Remind me to restart it when we go over the answers.
Yeah.
Okay, so let's go over it. All right. A bunch of you missed number 1. Why? The first part is correct, right? Interoceptors come from inside the body. What was wrong was the second part of it. Taste, smell, and temperature. Taste and smell are external. Okay? Except I'm going to give you an exception to that in just a little bit. Chemoreceptors are the most primitive. Most of you got that. All receptors are neurons. No, you could have a specialized cell. That's why it would be false. Maybe. Maybe. Thermoreceptor, or no, sorry. Sensation occurs in the cerebellum. What's the cerebellum for? Balance. But 25% of you said yes to that. Perception is the meaning. Almost got 100% there. A few of you just forget that one. 100% on 8. Good. Tell your bio buddy, would you be happy if this was a quiz score for you? Okay. All right. So, taste. On your tongue, it used to be thought of, and this is not true, okay? Used to be thought of, and did you get taught this when you were younger? Sweet being in the front, and then sour is here on the sides, sugar is like here, and bitters in the back. That has been in so many textbooks, it's totally not true, okay? The tastes are all over. I taught that for years. It was in books, you know? So I'm like, okay, you know? And I would do labs, and we would have the different flavors, and then their bio buddy, you'd have your eyes closed, and they would dip it in sweet, but they wouldn't tell you it was sweet. It was like a real mild sweet, so it wasn't overwhelming, because if it's overwhelming, it can actually trigger other things, just like cold and pain and everything. And so they would put it on different parts, of, like, mine doesn't match. I'm like, you're a loser. Okay? But it's totally not true. Okay? They're all over the place. Okay? So, and like we said, tasting is really more about smelling than anything. There's only 5 real flavors for taste. There's another one, umami, by a Japanese scientist. That's like meaty or broth kind of a taste, is umami. And what when people look at a tongue and they say these are my taste buds, those aren't taste buds. Those are papille. Okay, you got to say it like you're an Italian. papillae. And the papillae, that at the top, you got to go down the walls of the papillae. And if this were a papillae, it would be here on the sides, okay, is where the taste cells are embedded. So that's why you have to take your food and get it moist and chew it, and then it drips down the sides. When some people say you're eating your food so fast you can't even be tasting it, that's true, okay? Because you need to get it in solution, have it drip down the walls of your papillae, and then it will trigger it. That's why if you would eat it slower, you know, it would be maybe better. And if you go down the sides, here you will see that you have taste cells, which have the microvilli on it right there. And then here, these are just support cells. And again, this taste cell will trigger this neuron to fire. Okay, so on here is the misnomer. Okay, and again, that was taught forever. So, yes?
By old man, would that mean that like your minimum time can't eat anything?
No, what they would tell you is that there's a mixture here. And then I've said that this is just concentrations of it. And it may be concentrated for some, but not for all. That was just one of those things that was like perpetuated. It's the same thing where they use the examples. Have I talked to you about behavior already? I will talk to you about behavior. And in books forever and ever, they would talk about that monkeys could stack boxes in order to reach bananas. So they were learning, you know, and it's not true. That experiment's never been repeated. But it's like in every textbook, these monkeys stacking boxes, like a rendition, a drawing. Yeah, it doesn't happen. But anyway, we'll talk, it's called insight. When insight is when something you've never done before and you apply it to a new situation. So they would say, oh, that showed insight because they learned to stack the box in order to stand on top. Let me give you an example of insight just so you know. Insight would be like, this part is true. Meat hanging from a string on a branch. And a crow wants to eat that meat. So they go and fly by, but because it's tied to a string, it moves, right? So if they stood on the branch, crows will go down, pick up the string and stomp on the string with their foot, and then go get a little more of the string and stomp on it again with their foot to hold it until they've pulled it all the way up high enough where they can access it. That would be insight. Okay? All right. But anyway, it's one of those things. What I want you to see is, how do we know sweet, sour, bitter, umami? What's varying in those cells? What? They're receptors, exactly. Okay? So here, take a look. This is salty, and this is sour. Okay? And again, let's see, how are they the same? How are they different? We'll take blue, we'll take the first one. You're in charge of explaining how do we detect salty. Go ahead, Blue. Put in your own words.
The sodium from the salty food. And some calcium too. The same thing. Calcium makes yeah, it's just salt. No, you're eating salt, so salt goes to the
Okay, now, for taste, this first cell here in purple is not a neuron, but do you see something similar to a neuron in this? Okay, so here the calcium's coming in and triggering the release of a neurotransmitter. If you get enough of this, right, then you're going to trigger an action potential in that sensory neuron. That sensory neuron for tasting salty goes to a part of your brain that we know is salty. If you could move that neuron to sweet, then we would perceive anything that's salty as what? Sweet. Okay? Yes?
Would then this sodium channel be responsible for resting potential of this taste bud, or?
No, resting potential is the sodium-potassium pump.
Okay, so
this is not a neuron. This is a receptor cell.
So there's no resting potential.
Yeah. Now, if you look here, go ahead, Slate. You're going to do sour. Sorry, induce a seizure in you. Go ahead. How is it similar? How is it different?
Okay, this time instead of NA just different chemicals.
No. See what happens? No, Ori, no. You see, because the hydrogen that belongs to the potassium channel, and the potassium can't come out, it causes some big problems. That's why they say so.
So, salty food, what's the formula for salt? NaCl. So they would have sodium, right? So in the last one, sodium was coming in, which was then calcium was coming in, right? And then we had the release of the neurotransmitter. This time, hydrogen ions, and this is different. Hydrogen, because if something's sour, it could have a low pH, right? Acid, right? Lemon juice is acidic because it has a low pH. It's sour. We interpret that as sour. So hydrogen ion blocks what? Potassium from going out, which keeps it positive in here, which then allows, just like before it kept it positive, but that was because sodium came in, right? This is because potassium can't get out. Now it causes depolarization. You have that calcium coming in, and again, you're releasing a neurotransmitter. Same part here is the same. What's different here is the receptor. When I told you one of the learning objectives you need to know for the AP exam is how do we detect our external environment to trigger to perceive that. This would be a really easy example to remember because you know sodium, right, in salt, and you know low pH with something that's got a sour flavor to it. So, youngest bio buddy, listen as your oldest bio buddy tells you. How is salty and sour similar? How are salty and sour different? Go ahead. Hey, now, you know you don't have taste just right here on your tongue, right? Where else do you have taste cells? All on your throat, right? Right? But here's the deal. This is going to be a crappy picture, but it's because I snapped it with my phone. Why I didn't go over to my scanner, I have no idea. Okay? There are taste receptors all over your body. In your bone, in your brain, in your heart, in your lungs. Are those places where you have food? No. You know what they're tasting? Bacteria. They're tasting bacteria, and these taste receptors in other parts of our body are actually part of what they think is our immune system. Okay, and the way that you look right here, sweet receptors, okay, are in pink. Bitter receptors are in green in this picture, and both bitter and sweet are in blue. Okay, taste receptors in your gut. You've already eaten that food. Why would you need to taste it? What could be in that food that we're concerned about? Bacteria. Okay? So look at this example. Again, I know this is hideous. I don't know. I need an online version to this. Okay? So if you look right here, bacteria will release a chemical which we can taste. We have receptors for that chemical. Okay? And the chemical is acylhomoserine lactones. It's AHL. Okay? So that gets released, and this chemical is detected. This chemical is detected by bitter taste receptors from a group called T2R38s, which sit in hair-like projections called cilia that extend from cells on the inside surfaces of the nose. So you are tasting in the cilia of your nose. Okay, and the cells known as nasal epithelial cells release a gas, nitric oxide, in response. The gas diffuses into the bacteria, killing them. So, and so that is part of what you can see here, part of our immune response to bacteria. But the thing is, that's how we're detecting them. Our receptor is actually a taste cell. Okay. I could see something in the future, them having you write an essay on that, like scientists have discovered, and then you have to respond to it. So if it's this year, there you go. You already know about it. Yes.
Could they also be checking for
Sure, absolutely. This article was really, it was checking for even more. I'm just showing you one part of it, but absolutely. Okay? All right. So on taste, let's make sure we have everything we need for taste. You could add that to your notes because I didn't put it in your notes. But the brain determines taste according to the overall pattern of incoming impulses. According to the overall pattern of incoming impulses. So in that case, taste cells trigger neurons. Okay, smell is different. Whereas you have 5 main tastes, blue tells slate the 5 main tastes. Umami. No, umami. Okay? Umami. Okay? Meat or brothy taste. All right. Where we have maybe 5 different tastes, smell, you can detect, 1,000 probably different smells. And some people really work to hone that, right? People who are like wine connoisseurs, they take the wine, like when they do their tasting and they do this little gurgly thing, and then they spit it out. Not me. At the wine tasting, I'm like, delicious. Okay, why are you spitting it out? But they'll go through it and they can go, oh, I taste honey from an oak tree. This has got to be 1983, and that particular oak tree was next to a lilac bush. And they can determine that. There are professional odor people, literally, who smell people's armpits with deodorant, and they can detect different things. People who are making perfumes and combinations, they see perfume like you would, those my musicians out there, they see smell like the same thing as notes. They call it notes. And they put different, just like you can in a song, put different chords together. When they're making perfumes, they're putting different notes together in order to create some sort of smell, okay? And some people some people wear more musky smells. Some people might wear fruity smells with a hint of cinnamon. I don't know. Vanilla. Now, spicy probably has most to do with pH and the hot. And some of you, where are my spicy food eaters? Right here. Okay. So I'm going to tell you right now, I can't handle it at all. And if it's too spicy, I feel I will choke and stop breathing. It's like I have some psychotic reaction to it, and I have to drink water, and I'm afraid I might die. And it could I have to pick out all the little red flakes if you get the, what's that one? Yeah, definitely. I'll put a little on there. What's that Chinese food with the chicken and the little water chestnuts or shrimp? Kung Pao. That's what I call it, sorry. It's like, I'll say to him, or the pepper's like, oh no, you can see them. Well, I understand the big ones, I can move those, but when you ground it up in there and I can just see the red, I'm like, death, death, death. All right. Yeah, I can't handle it, it's terrible. And then some people say, like, I saw Mr. Martin yesterday who had some chicken that was hot chicken. All it was then at the end were peppers. And he was just eating the peppers out of it. What, that is so good to you? Yeah. What is good? He goes, he goes, later I'll pay for it, I'll fill. I'm like, why'd you eat it? No. Okay. Anyway, when we smell things, it's an actual chemical binding, okay, to a sensory neuron. And we can smell like 1,000 things. A dog can smell like 10,000 things. Okay? We can't differentiate as well as a dog can. Like they can smell fear. I'm sure they can. Because we're going to secrete a hormone when we are fearful, and they can detect that, right? All right, now, when it binds, it's a combination, again, like taste. Yes?
How would they detect the hormone inside?
If you are emanating it, and it's a chemical, it's going to be in my blood supply. And if it's a blood supply, if it could be gaseous, I could, yeah. Okay, so, when you smell something, okay, you're bringing that gas across your nasal cavity, but right here, what's used by both your respiratory and your digestive tract? Your pharynx. So, right here on Fang Boy, there's a tongue. And so when you are breathing and smelling something, it's also binding to receptors on your tongue. So whenever you smell something, you're not thinking about it, but you're also tasting it too. It'll bind, because if it travels in the air, it will travel across your tongue, which grosses me out, because there's some things, you're right, you're there. You don't want to smell, right? Something you don't want to smell, like if somebody's baking brownies, so to speak, you don't want to smell that brownie. That brownie, there's literally a chemical that's now on your tongue that was in somebody else's body. Right? Same thing with smelling. That chemical that was in somebody else's digestive tract is now on your tongue. Okay? Now, do things taste different than they smell? Can things taste different than they smell? Yeah, because we only have 5 different tastes. So there's going to be a little confusion there, because if you take perfume and spray it, you're like, oh, it smells so good. Let me spray it in my mouth. It doesn't taste that way, right? So there's different receptors. All right. So on smell, molecules bind to receptor proteins on the cilia of neurons called olfactory cells. Olfactory, it's below, 2 words below. It looks like old factory without the D. Olfactory. It's an olfactory. Okay, and then olfactory bulb connects directly to the brain, to memory, and to emotions. And this is also why you shouldn't snort things like drugs up your nose, right? Because that chemical is going to a neuron. And then have people ever snorted things and then had brain damage? Yes. Okay. And seizures. So this is going to your limbic area. Remember what we learned about limbic? What's limbic? Emotion and memories, right? All of that. So smells can trigger those memories. Those smells more than even taste or vision sometimes. Some people have done studies where while they're learning material, they'll burn a vanilla candle. And every time they learn, whenever they're studying, they burn a vanilla candle. And then you come in during the test and you burn a and it help you with memory. Feel free to try. We just have to agree on the flavor. Okay? Because if I'm smelling, hibiscus, it might override my vanilla that I learned on. Okay? But you could do that. What? Oh, chewing the same flavor gum, maybe? If you're going to do it as a class, you got to agree on the flavor.
We should totally do it.
What? You want to try it? Okay. All right. No, cocaine is not a flavor that you're picking. All right. Yeah, that was Dory.
Good times.
Oh, good. Somebody did it again. That's awesome. Or it's the same person.
see, dude, if I wasn't dating ASB, my life would be great.
I don't want them to do the
Okay, I can't wait any longer. Okay.
It's okay, dude.
Okay,
The last
so
one.
5 of you got it right. Who picked only B, C, and D? Okay, good. Nobody picked A. I'm glad. Some of you forgot B. Chemoreceptors are a primitive sense. Some of you forgot C. Fly feet can be used for tasting. Did anybody forget D? One person did. E is what some of you screwed, 12 of you screwed up on. Sensory neurons are the receptors in both nose and tongue. Sensory receptors, right? The sensory neurons are only in the nose. There are taste cells in the tongue. Yes?
I was a little bit confused on why B is correct because, I mean,
Why what?
chemoreceptors-
What?
B, why choice B is correct? Because chemoreceptors themselves, they aren't a sense themselves, are they? They're just
Yeah.
receiving the sense.
No, yeah, no. Chemoreceptors and smell is the most ancient and most primitive. It's where a chemical is binding to the surface of a cell and triggering a response by that cell. That would be before a photoreceptor or a mechanoreceptor, right?
No, I understand the primitive part. I mean,
Oh,
I didn't
I'm
think
sorry.
I didn't think it's a sense itself. The receptor
No,
itself
it is. Your nose is a chemoreceptor. Taste is a chemoreceptor. Yeah.
Oh yeah, please send that.
All right. Now, oh crap. Sorry.
It's just it sucks a lot, you know.
Okay, and then the next question.
See, now it's something-
Only 2 of you missed this one. So you do activate different sensory receptors. Most of you got that. 2 of you picked. None of these are correct. Awesome. So yeah, sweet versus salty is a variation in the receptors. All right. Next, do I have everything? Did I get smell? Did we do it? Yeah. Okay. So vision. So there are different kinds of photoreceptors. Photo meaning light. Okay. A compound eye. If you're going to give an insect a contact, you know, to correct their vision, you would need to buy them like 20,000 contact lenses to put on each one, because each one of these, they're like rhabdomirs, each one of those has a lens, okay? And they see in a light bright fashion, if you remember what light bright is, where you would put in the different colors, okay? That's how they see, and that's why they can detect change, because if one of these goes out, they can see that difference. They can perceive that one difference. And that's why it's hard to sneak up like on a bug or a fly or whatever, because they see that one difference and that's their startle response, okay, to make them respond. Okay. Where this is what it looks like. So each one has a lens. And they see in UV, okay? So they see in light that we wouldn't necessarily perceive. We have what's called, though, a camera type eye. You see it in an octopus, you see it in a mammal, but it's a result of what? Convergent evolution. And this is where we take light and direct it onto a surface. In this case, we're putting it onto rods and cones. And then we're taking that image, and it's flipped upside down, but we make it go, we use our brain, and we figure out it's right side up. And then there's different places where you place your vision. So we have forward-facing eyes, and the vision overlaps from each one, and our brain puts the pictures together so it appears as one picture. Whereas panoramic is on either side, so they want to. For them, it's more adaptive to see more of their view, probably because they're what? Yeah, they're prey. Yeah, so they want to be able to see more. Now, we have, we can have far and we can have close vision. So for us, fish will take their lenses and move their lenses in and out just like you would on a camera to zoom in. What we do to zoom in is we bend our lens. And there's little ciliary bodies, and we'll flex it. So what I want you to do is hold up one finger kind of in front of your nose, but I want you to look at a distance. Everybody look at a distance. On the count of 3, I want you to look at your finger. 1, 2, 3. Now stare at that finger. Is it sharp to you? Okay. On the count of 3, we're going to look at a distance. 1, 2, 3. Did you feel it relax? Okay. So what happened there is, to look close, you have to round up your lens, and then you relax. Well, here's the problem. I'm 50. I'm 50, okay? And so what happens is my lens is older than your lens, okay? And by 35 plus years for some of you. So that lens has been working for 35 years, flexing. Now it's like, screw it, okay? And it won't do that anymore. So when I look right here, my finger is not sharp. Kinda, okay? And this is when you start to lose that ability. So if I'm in a restaurant and I'm like, this is where you see people with magazines or newspapers, your grandma or your parents, and they go like this. Well, it got to the point where you would have to hold that menu across the room before I could ever see it, you know, in order to make it sharp. So that's why people, as they age, start to use these, because we all start to lose that ability to flex our lens. This is different than being nearsighted or farsighted. Where are my people who can see at a distance? Raise your hand. Distance, but you can't read close. Okay, so what happens is your eyeball is too short, so it doesn't come in to be sharp right away. And then where are my people who can read close, but they can't read far? Okay, so you are nearsighted where she is farsighted, right? So the problem with you, and was with me, our eyeballs are too long. So when the light comes in and gets sharp, our retina is still over here. So it starts to disperse before it gets to our retina. So what you can do when you're older, what I had done, which was awesome, you know, was I had part of my eyeball shaved off. So what they do is they take a flap of your cornea, right, and then they use laser, and then all when you're awake, okay, that's another old story I'll tell you, and then they flap it back down. You feel pressure when they slice open your cornea. They like clockwork orange open your eye, and then they put this suction thing on, and then they come across with a slicer, and they make a flap on your cornea like this. And the nurse will be counting down, because you can't have your eye exposed for too long without the blood supply there. So you'll hear her go, 10, 9, and you're like, big sigh, you know. And so they have it flapped open, and then you can't see, because the other eye is like covered. They can't see, and then this red light, like, come to the light, starts going, and you can hear it, and it's burning, and you can feel it sparkle onto your face. And this is the moment where you go, what? You know, and you're like, but they've given you a couple, they had to give me more than one. They're like, let's give her a little more, you know. And then they flap it back down, and then they use a little paintbrush and make sure there's no air bubbles, and then they go and do the other eye. And if I hadn't paid $1 billion, because you don't want to go cheap on that, okay? Pay a lot of money if you're going to have something done to your eyes. Don't go somewhere cheap, like, oh, I can do it for $500 each eye, sign me up. No, okay? Get a good doctor. Okay, and then they do the other. And if I hadn't paid so much money, I would have been like, stop, I'll do one eye. You know, but anyway, it's fine. All right. So those of you that are nearsighted, you can have your vision corrected, because they can make your eyeball shorter. That's what they did to me. You can't make your eyeball longer, so you guys can't have that surgery done. Okay. This is blue sclera. This is when the white of your eye appears blue. It's a genetic disease, just thought I'd show it to you. The light shines here on your rods and cones. You don't have to memorize all of that. Oh, sorry, yeah, that's cool. Okay, what do you see? All right, go on to your notes. On anatomy and physiology, the inner layer is the retina with rods and cones. Yeah, what number is it? 16. What did he see? What did you see, Max?
It was like a 33, but backwards 3s. No.
I love it. Okay, now, do you remember how plants detect lights? PFR and PR, right? And it was like a toggle switch. Same in us. Conserved process. Retinol. Toggle switch. That's why if you get a really bright light, like you look into an overhead projector or something and then you look away, you can still see it. It's because it's overstimulated it into that one space. Now this is what I want you to see. In your rods and cones, in your retina, light has to go through all of these layers. Your rods and cones are the farthest in depth. And light has to pass through all of these layers. Then the action potential comes back out. And where the nerve leaves your eye, that's the blind spot. And you can find your blind spot with one eye closed, and I can show you how to find your blind spot. But you don't notice your blind spot when both your eyes are open. Why? Yeah, this one will take care of the other eye. Yeah. Okay. Okay. Good. Let's go on with hearing. On your photoreceptors, rods permit vision in dim light and black and white. Dim light, black and white. Peripheral vision and motion. And cones permit vision in bright light, color, red, green, blue. And cones are good for fine details. For hearing, again, mechanical, light, tympanic canal, Malasinca stapes. This is your cochlea right here. There are two canals, one folded back on itself, so there's actually appears to be 3 canals here. Inside here is the organ of Corti, which I'll show you in just a minute. These semicircular canals are perpendicular to each other. This is angular movement. This is how you detect that. You have in this area right here what's called a utricle and the saccule. The saccule helps you determine that you're moving up and down, and the utricle helps you determine that you're moving side to side and your perception of that. And then angular are those semicircular canals. And then hearing is right here. And if you go into that ear, okay, and you took a cross section out right here, it would appear as if there's 3 canals, but these 2 are folded back. Right here is the organ of Corti, which is where you actually have hair cells embedded, and that triggers your ability to hear. So go underneath 3 inner ear, cochlea. Hearing, the functional unit is the organ of Corti. Organ of Corti. And then you have semicircular canals, right? Yeah. Utricle and saccule detect horizontal and vertical movements. You have that? Oh, that's what I just asked you. Semicircular canals is rotational equilibrium. Rotational equilibrium. And then utricle and saccule detect horizontal and vertical movements. If you go down into the steps of hearing, if you look at number 8, hairs are embedded in the tectorial membrane at the top, and so hairs bend, which causes an action potential in the cochlear nerve. So hairs bend, which causes an action potential in the cochlear nerve. Action potential in the cochlear nerve. Okay, this I've already talked to you about. Proprioceptors. Number 2, involved in reflex actions that maintain muscle tone. I'm sorry, you guys. Reflex actions that maintain muscle tone. Last thing I need to get, if somebody has a heart attack, where do they feel it? Left arm. And what do you think people think that pain is a result of? Improper circulation props because you have a heart attack? It's not due to any of that.
Attention seniors, bring your lunch to the College and Career Center right now.
Okay.
For the Moore Park College application workshop.
Your brain can't tell sensation like it can the skin. So when your brain gets tremendous pain, Ori, from your heart, it just arbitrarily goes, it's your left arm. And it throws it to your left arm. That's called referred pain. Look right here. The left side of your neck is if you have issues with your lung and your diaphragm. The right side of your neck is liver and gallbladder. Your brain just goes, I don't know where it's coming from because it's coming from internal, so it throws it somewhere else. If you're having trouble with your kidneys, you're going to feel it in your hips. Your urinary bladder right here. Oh well. Okay? So this is referred pain. It's your last thing. Felt in your left arm on pain receptors. Felt in your left arm. Felt in your left arm. All right. Be good. Have a piece of toast.